Okay, good afternoon. So we're starting lecture 10. So what we have done until now, you can see the list: introduction, 3 lectures on regression, and then 5 lectures on SVM, and then we'll have 4 lectures on distance-based models. What are distance-based models? We'll do classification and clustering there. So if you recall the first lecture in machine learning, what we said was there are 3 components. One is the tasks, which you're trying to solve, then there is features, and then there is models. So features we are not explicitly focusing, and task is something this will come from your survey paper which you're trying to read the other papers. But in the models we are focusing on. So we have seen regression, SVM, now we're seeing distance. These are all class of geometric models, and then after the midsem with Chandresh, you'll see probabilistic model and logical models. When you say probabilistic models, some of these models which I am teaching you, they will have a probabilistic connotation as well. So regression, there will be logistic regression, which is a probabilistic model. You would have SVM, which could be seen as a probabilistic model. You also have classification and clustering, which will be probabilistic. So all the models which I'm teaching you, they can have a probabilistic view as well. So that is why there's so much of machine learning is statistical or probability based. So that you will see with him. Logical models is simple trees, which you would, one of them is decision trees, which you would see. But today the focus is now on distance based model. So the goal is today and tomorrow we'll learn what is distance metrics. In case you are a math major, you would know how to define a distance metric. Others probably don't, so we'll define it more explicitly because different distance metrics are used to do all kinds of computation here. The second thing which we will do is we'll do simple classification using these distance metrics. So that is what you would see today and tomorrow. Tomorrow, half of the lecture is classification, then we'll do 4 problems. So you'll get more started with it. Then Wednesday is your quiz only on SVM and regression. There'll be, I don't think you can bring your calculators. I don't think there'll be any deep calculations, but still there may be simple computations which you would have to do. So that's one thing you would do. And then Thursday, I've uploaded. So these 2 lectures are uploaded already. So we are coming close to finishing. There are 2 more lectures. Usually there are 12 lectures, half of the class, because rest is tutorial. And class level recording. So tutorial lab, these 2, there are 2 examples which you will do Thursday. This will take half an hour, 40 minutes. They're not, because you'll do some problems with me tomorrow also on distance based model. And then you will implement a k nearest neighbor classifier in Python on that. So these 2, 6a and 6b, I'm trying to finish it in one go, so that you don't have to wait too long. Then more offline material I'll upload after tomorrow's class. Supporting material, there is some more supporting material which I'll upload. Practice, have you seen SVM practice? Have you gone through that? We'll upload the distance based practice also after this. And then homework, there's one homework which I'll refer today, distance Chebyshev, which you can go on your own, but there'll be many others which I'll upload. Okay, so without further delay, let's start the lecture. So the goal, like I said, would be to define few distance metrics. Okay, so this is the goal. These 3 we'll do today and tomorrow, and then clustering based analysis we'll do the following week. Then that is how this will finish. Where's Ayush? Achha, he's on leave. All right. So the most general form of, is it readable, right? Is it readable at the back? Make it bigger. No, not readable. Is it readable? Okay. So what is Minkowski distance? So basically you have x and y are 2 components of your input space, and then you component wise you take the difference, you take the norm, put it to power p and take the pth square root. So that is what is Minkowski distance. The most common one which you see is the Euclidean distance. If p becomes 2, what do? we take distance wise, component wise difference, we square them, we add them, and we take a square root. So Euclidean distance is something which we are most common, but you can do it for higher norms as well. So the Euclidean distance also can be written as an inner product of two vectors and then taking a square root. This is something you know. Euclidean distance is distance which the crow flies. The shortest distance between two parts is called the Euclidean distance. So that's one thing. This is more general. We'll see more examples as we go along. It's not more useful. Sometimes difference distance measures, usually we only use 2 and 1, which you will see in a minute. You can do 3 and 4 also, but they would have other applications. So we'll go along, as I go along, I'll tell you. Right? Okay, so if P is equal to 1, then it is called the Manhattan distance. Why is it called the Manhattan distance? So if you are somewhere on the grid and let's say this is your 1 point and this is your second point. Let's say I'm in the 2-dimensional space. So this is let's say 1, 1 and this is let's say 3, 4. For example, this is your x, vector x, and this is vector y. So what this distance metric is doing, it's taking the component wise difference and then adding it up. So this will do 3 minus 1 absolute value plus 4 minus 1. Correct? So that is 2 plus 3, this is equal to 5. Correct? So if you want to visualize this, how this is doing, this is first 3, this is 3 and this is 1. So saying find this, move this much distance, and then this is 4, this is 1. So this is, well, doesn't look like 4, but this is 4 and 3. So now 4 minus 1. So basically you're going along the axis. So when you're going along the axis, then you're going like a city block distance, because Manhattan as a place in New York City is based on a proper grid. So that is why it's also referred to as the Manhattan distance. But it's P equal to 1 norm, right? So usually we use only these two, but P less than 1 and P greater than 1 are also sometimes used. Okay, so that is what Manhattan or city block distance is. Now what if instead of this was P is equal to 1? What if P tends to infinity? I cannot write equal to infinity, I'll write it tends to infinity. Then we call it something as a Chebyshev distance, and then you realize the summation vanishes away. Only the maximum of the component difference dominates, and the proof for that is done as part of the homework. There is some basic calculus used. So that's what I would say, you go home and see if you're interested. Offline and homeworks. So this is what Chebyshev distance is worked out. So basically there is limits are being used, and then there is a squeeze theorem of functions which is following. So you can go through this and understand this on your own. Something which you are not going to use it often in this course, but you should be aware. Okay. 1, 2. Where were we? Okay. So we were at the Chebyshev distance. Now sometimes when P is equal to 0, so we are doing all variations. P is equal to 0, P is equal to 1, P is equal to 2, and greater than P, greater than 2, for example. So when it is a 0, this refers to that you're finding, it's defined that way, that you're finding where the components are differing from each other. So it counts the number of non-zero elements in a vector, which means that the number of positions in which x, y, and differ. So this is not strictly a Minkowski distance. However, we can define it this, that where they are different. When you've got two binary strings, so P is equal to, so what we are writing here, we started with P is equal to 2, which is Euclidean, which you are aware P is equal to 1 is the Manhattan distance, which by now you go to P is equal to infinity is Chebyshev, which you can read, and this just gives the maximum value. Here it's adding this. And when P is equal to 0, let's say you've got two strings 0, 1, 1, 0, 1, 0. So now what will be the distance between them in terms of this zeroth, or which we refer to as the Hamming distance? They are same at the first, they're same at the second, they're differing at the third. So there's only one difference. So the distance metric here, distance 0 between these two is equal to 1. That is what we are doing. We use that in computer science, those who are there, how to see where the binary strings are differing from each other. Everybody okay with the distances? Okay. Now question comes, which I'll not show you the slide. We want to tell which of them is defined as a distance metric and which is not a distance metric. We want to check that. Now what is a distance metric? So in mathematics, when we go about defining a metric, a measure of something, then we define certain rules, right? So a distance metric is one which has 4 rules. We say a distance matrix, which says that the distance of a point, let's say O point, with itself should be 0. Correct? Everybody agrees? The second should be the distance of a point with another point which is not same. If origin is not same as A point, it should be non-zero. Everybody agrees? Intuitive metric. Third is that if you're doing 0, A, it should be equal to A, 0. It should be commutative between the two. Is that okay? And the fourth one says is the triangle inequality. That if you go directly to a point, that should be the shortest distance as compared to you go to another point and go to that point. Correct? So which means that, let's say I'm somewhere here and here and here and here, for example, these are my points. This is my 0, this is C, this is A. So say if I go from 0 to A to C, and I go directly from 0 to C, that 0 to C should be less than the sum of the other two directions. So you've got the triangle inequality. So the triangle inequality says that the distance I don't know why I'm using P, but this what I meant was the distance metric. It's a function which we are trying to define. So the triangle inequality says that the distance which you go from 0 to C should be less than the distance which you go from 0 to A, and then you go from the distance from A to C. It can be equal also. It need not be, which we'll see in a minute, that sometimes it may become equal. Everybody okay? Comfortable? Okay. So now what we're going to do is, there is a visualization of these which is done and which tells you which one is a distance metric and which one is not. So typically we are playing with P equal to 1, 2 and less than, because P equal to 0 is technically not a Minsky distance. This is something we have defined it in computer science, basically where the components are differing. So we're not going to worry, but if P is less than 1, then what happens? So we'll do 4 cases. So let's say we were doing the Euclidean distance. So the Euclidean distance, we were doing P is equal to 2. So the Euclidean distance will be what? It is this, right? So the distance is, let's say, working in 2 dimension. Let's say I'm at the origin. Yeah. I think ये अभी तो what I know is it mentioned anywhere? It's defined for real. I don't know about complex. I'll have to see because complex may I don't know whether the notion carries over or not. I'll have to check. Abhi for the moment in this one it's all real. That's a good question. What's your name? Come. Question. Good. At least a question came. So we have 4 more chocolates. You have to keep asking. I'll let you know. I'll check and let you know tomorrow. Come. Yeah. So where were we? So the Euclidean distance. Let's say I'm trying to draw how the Euclidean distance goes for some point which is at the origin and which has a radius 1. So if I have to draw the picture of this pictorially, so I would say this is x minus 0, one dimension, plus y minus 0, this square is equal to 1 square, or square root of this is equal to this. Correct? If I am trying to find the distance of a point away from the origin, which is one distance away, this total distance. Is that okay? If I am trying to draw, if I'm here at origin 0, 0 and I am trying to see what is the equation of the line. This you know it, but I am trying to tell you because for the others it's not intuitive. So I'm just trying to show you for Euclidean, then we'll do p equal to 1, then we'll do p less than 1, and then you'll see p less than 1 will not be a distance metric. The other two will be a distance metric. That is what way we are going. So there is this point which we are saying x comma y. We want to write the equation where the distance for this point is 1 everywhere. So this is what? This is an equation of a, correct? X minus square plus y minus origin square is equal to 1 square, or x square plus y square is equal to 1. So this is an equation of a circle. So if I have to draw a point which is of unit radius, so this will be one circle which will define any point which is 1 unit distance away from the origin. Correct? Similarly, what we could do is, let's say we have to draw a point which is 2 unit distance away. Sorry, square root 2 unit distance away. So this would be something like this, or even 2 unit distance away. I don't know how much that is. You can find it out. And then what we do, we make the center here, and we draw another circle which is unit distance away from this. So this is okay. So this is a point A, we call it. This is a point B, we call it. And let's see how this is drawn. This is a unit distance C point somewhere here. Okay. So let's try to see from this figure if the four metrics are getting satisfied or not. So this is a unit distance 1 circle, this is a unit distance 1, and this is a unit distance 2 circle. Is that okay? So so the question is, if you are at the first point, first distance metric with itself is 0, origin distance would be 0, so that is satisfied. With origin it will be 0 of origin, so that is satisfied. The second was, if you go from here to here, this distance would be 1 metric, right? So distance of 0 to A would be 1, so that is greater than 0, so that's satisfied. Third, if you measure from here to here or here to here, it's same. So these three are trivial to do, but we are still doing it. Once at least I am writing a comma 0, which will be 1, so that is satisfied. The fourth one is more important. So the question is, what is the distance of 0 to C? And then what is the distance from 0 to A? What's the distance from 0 to A? 1. Distance from A to C is? That's also 1 because it's 1 radius circle you have drawn. Now distance from 0 to C is how much? No, it's not 2. 2 is here. It is less than 2 and greater than 1. Correct? It will be root 2. Basically, from the figure I am trying to say, I am not computing it. So if I look at the figure, if this is 2 radius and this is 1 radius, then this distance would be less than 2 because it's between the two circles. From visually I am trying to tell. Since it's between the two circles, it is less than the sum, hence the triangle inequality is satisfied. Everybody okay? This we are doing because we'll do for other p's where it's not that evident. So now let's do it for p is equal to 1, which is the Manhattan distance. Okay. Why are we studying this? We are studying this because the next thing which I'm going to tell you is exemplar. What is an exemplar? It's the representative point of a set of data points. For example, centroids, you have heard, no? You hear it in mechanical. Or medioids, you keep hearing. So when you're trying to classify a set of data points into different classes, you have to figure out what is the representative point of that data point. To figure that representative point, you have to figure out the distances which they are from each other. And their distance, different metrics are used. Again, p is equal to 2 and p is equal to 1 are the most common one used, but p less than 1 is also used and p greater than 2 is also used. Right? Okay. So that's the reason we are studying. Everybody comfortable? Okay. Questions? So now let's do the case p is equal to 1. So p is equal to 1, what will be the Minkowski distance? Again, we are somewhere at the origin. We have to find a point x comma y which is 1 unit away, but in terms of p is equal to 1 distance. So what will be the Minkowski equation for that? So that will be x minus 0 plus y minus 0, 1, 1. There will be no square root because the power would be 1 over 1 and this is equal to 1. Correct? Everybody with me? So this will be x plus y is equal to 1. Correct? Which means that if you have to write y absolute value, this will be minus x plus 1. Is that okay? Now we want to draw this. Let me make it slightly bigger. Because I want to answer the same things which I answered earlier, I will draw this figure. So we are at 0, 0. So now let's say this is x-axis and this is y, which we know, which we are following. If both of them are positive, this is y is equal to minus x plus 1. What's the slope of this? Minus 1. Tan theta is minus 1 when it is 135 degrees. So it will be slanted like this. Yes or no? Or you can put x equal to 0, you get y1, y equal to 0, you get x1. Correct? If both of them are positive. So, which means this will be the equation of the line in this quadrant. Everybody agrees? This is the angle, this is theta, which is equal to 135, tan 135 is minus 1 and that's why it's minus 1 here slope. Okay, so now when we go to the left quadrant where x is negative, if you put x is equal to minus 1, what do you get? What y value do you get? If you put -1, it will be 0. So it will be here. And when you put y is equal to 0, sorry, when you put x is equal to 0, you get y is equal to +1. When you put y is equal to 0, then you get x is equal to -1. Correct? Which means that you can, and if you put, let's say, x is equal to a -half, then it will be +half, -half, it will still be positive. So it will go like this. Everybody with me? The rest you can draw, which means that it will be a tilted square or something like a rhombus, or not exactly a rhombus, but yeah, a tilted square, because the angles are all 45 degrees. Correct? Everybody with me? Now let's do the same thing which we did earlier. We will draw a bigger one. So this is distance 1, which means that everything on this slanted or rotated square is 1. The distance from the origin is 1. Correct? What we'll do is we'll draw another one which is a distance 2. And then we'll also draw one which is centered here. So this I am calling as A, this point I am calling as B, this point I am calling as C. So now we'll do the same argument by looking at the figure. So the first one is the distance of the origin with itself is 0. So that's correct. Second we'll write is the distance of origin with A, which is equal to distance of A with origin, because it's 1. So that's correct. The third thing which we write is, no, sorry, distance second was that the distance with the A is not equal to 0. So this is equal to 1, which is greater than 0. The third one was distance of A with A0 and distance of 0A. Both are equal to 1. Fourth one is the most important one. What is the fourth one? Now you tell me what is the distance of 0 to C? Root 2? This is 1, this is 2. 2, everybody agrees it is on this. I've made that circle, I can make it square root 2 also. I'm just showing you the difference. So I made a distance 2. So everything on this rotated square is 2 units away from the origin. So the distance from 0 to C is 2. Now if you do distance of 0 to A is 1 plus distance of A to C is 1. So this distance to the 2 are equal. So the triangle inequality is satisfied. So again, P equal to 2 is a distance metric and P is equal to 1 is also a distance metric. Can everybody understand? Now we'll show you, yes. Distance 2 is equal to means that this distance instead of 1 I am making it 2. P equal to 1 is the norm or the power which you are using, that's 1. The distance 1 initially I made equal to this distance. This guy I am making it 1 and then I am making this 2. Is that okay? If I don't make it 2, then this guy will not fit here, because this is distance 1 everywhere with center at A. That's why I had to make it 2. Is it making sense? Doubt? Ask me. चॉकलेट भी है ना, पूछ लो. मुझे खत्म करनी है आज. What's your doubt? Correct, because this is on the surface of this rhombus of distance 1 and this is on the boundary of this rhombus centered with distance 1. OAC, it will form, but it will not form in the correct. That is what I am spending so much time. This is norm p equal to 1. This is not Euclidean. If it was Euclidean, then you were able to do this square root distance which you are so used to. That this minus this square plus this minus this square root is equal to 2. That definition doesn't work here. Here the definition would work is this definition. That OAC will form this is 1 and this is 2 in case of the distance metric p is equal to 1. This will not be this will be equal to square root 2 in case of p is equal to 2. That is what I'm going to say. When you change the distance metric, then the figure looks similar, except that here you have a rotated square. We don't have a circle here, right? I mean, if I was at 2 distance here and I had to maintain a 2 distance here, then I will go around this like this, right? You can see it's not doing in the Euclidean case. Is it clear? Okay. So now you realize that this distance is 2 and this distance is also. I don't know which is a better way of more explaining this. Sorry? No, triangle will form, except that the triangle inequality will be exactly equal. So this okay, let's write it more explicitly. So in both the systems, p is equal to 1, this will hold. Except the difference is when you've got p is equal to 2, this distance metric will be square root 2, and this will be 1, and this will be 1, and this will be less than this. When p is equal to 1, then this distance metric is 2. It will still be equal to this, guys. The distance metric, because you're changing, that is why the values are changing. Think of if I have to write this c value, so that will be x minus 0 square plus y minus 0 square is equal to 2, right? Square root of that, this distance is equal to 2. And in the other case, we are saying x minus 0 plus y minus 0 is equal to 2. So we're saying x plus y is equal to 2, or y is equal to minus x plus 2. Sorry, what are you confused? No. That is in the Euclidean distance. That's what I'm trying to tell you. Because your visualization is all about Euclidean distance. In terms of other distances, you can't visualize them. So that's why it's trying to tell you that. The metric is different. Look at this. If I just put square root of this is equal to 2, sorry, this is equal to 2, then you get this kind of a surface. you get that this is the line 135 degree and then this is equal to 2. All the visualizations which you are trying to do are all for Euclidean distance, because that is what you normally see. I'm going from here to here, so I'll say this minus this square plus this minus this square plus this minus this square, square root of that is equal to the distance. But when you go to other metrics, you can't visualize this directly. Is that okay? Anybody else confused on this? Clear? Okay. All right. Kuldeep, ek minute keh dena, I'm in class. Somebody's calling. All right, so now what we do is, okay, the third thing which we do is if p is less than 1, let's say p is equal to 0.8. So we are, cut gaya kya? Acha, bol diya. Okay. So if let's say p is less than 0.8, then the figure comes out something like this. Rather than being an exact rotated square, if I have to draw this, it becomes like this. Of course, you can work out the equations. इसको क्या हो गया? Okay, before I go ahead, let's write this down. So let's say if p was 0.8, then the equation would be x minus 0 to power 0.8 plus y minus 0 to the power 0.8 and whole to the power 1 over 0.8 is equal to 1. Is that okay? So if I try to draw this, it will turn out to this. So this is 1 and this is 2. Okay, and you can use a computer and put some points and you'll see that it's not a straight line, it's curving inside. Now if I have to draw this with the center here, it will go something like this, come back like this, go something like this. Maybe I draw with a different color. और तेरी क्या हो रहा है? Didn't like it. इसी से करते हैं, चलो. Go like. So this is again A, this I call it as C, this is call it as B. So again, this is a distance 1 away, this is a distance 2 away, and this is again a distance 1 away from A. This smaller rhombus. The same idea, correct? So if I apply 1, 2 and 3, it will be the same like we did earlier, so I'm not going to waste time. With itself is 0, 0 to A is A, 0 to A is positive 1, 0 to A is A to C. The fourth one if I have to do, so if I have to say what is the distance of 0 to C, what is it? Greater than 2, because it's going outside this. Correct? And now if I do distance of 0 to A plus distance of A to C, distance of 0 to A plus distance of A to C, this will be how much? This is 1, because this rhombus or this figure is also distance 1 from A plus 1, this is equal to 2. So is this distance less than this? No. distance from 0 to C is turning out to be more than the distance going from 0 to A and A to C if you add them up. So this is not a distance metric. Does it make sense? Now it will be more clearer that you can't always visualize it. In this figure you may now feel that why is this distance more, because we are not going in straight lines, we are going on curves. Everybody okay? So P is equal to 1 is a distance metric, P is equal to 2 is a distance metric, but P less than 1 is not a distance metric, so we don't use it. P equal to 0 is used in computer science, in Hamming distance and other things which we use a lot in data structure. P greater than 2, where is it used? I'll get back to you, because I am also not aware, coming to your question, where it is useful. And about whether these can translate to complex number, my gut feeling is they don't, because we are working with distances which usually in real life are all reals. So I don't know, I don't think it will work for complex, but I'll check and I'll let you know also a case where P is greater than 2 works. But for the rest of the course, we are going to focus on P equal to 1 and P is equal to 2, because we have shown them to be distance metric. Everybody okay? Yes or no? Okay. Hey, you can take this. You asked a question, I forgot. I have to finish this also. So whatever I talked about is here. So this is what is summarized here. Yeah. And now what we go is we do another proof. What's the time? It's already 2:18. Okay, this one proof which we want to do. I have already done it here, so I can go over it with you. If you want, I can write it also here. So the very first, so now what we are doing, we talked about different distances. Again, I've summarized it for you. We'll focus on 1 and 2. Less than 1 is not even a distance metric, so not used. P equal to 0 is a special case. P greater than 2, where it's used, we'll tell you. I'll check and let you know. So we come to neighbors and exemplars. Now why are this distance metric used? These are used to figure out a representative point of a set of data points. And that is how we do our classification. That is where we are going. So to do that, there is this first theorem. This theorem says, make it larger for you. Okay, now I can't read. So is it readable at the back? Deepak, right? Yeah. So the arithmetic mean of a set of data points in a Euclidean space is a unique point that minimizes the sum of squared Euclidean distance to that point. So basically, look at this guy. If I'm using, if I'm given 10 points, so if I'm given, let's say 1, 2, 3, 4 points, and I have to find a point which minimizes the Euclidean distance from all the other points. In fact, the square of the Euclidean distance. So this, every component wise, this minus this square plus this minus this square plus this minus this square, you add them for all the data points, for all the components. Then that would be, if you had taken the mean of this, that would be. That is what we are trying to prove here. That if you take the mean of all the data points, it will be the minimum of the square Euclidean distance from that point to every other point. So this is what is written here, that if you take x minus y, and y is something which you want to figure out, so these are your x's and this is your y. Then if you take the two norm and sum it over all the data points, and you've argmin just means that it's the argument which minimizes this. So x is known here, y is the argument. The argument which minimizes this function is mu. Mu is the mean of the given set of data points. Is that okay? So we have to prove this. So I've worked it out, I'll show you. Okay. So we'll come back to this slide. I'll work it out here because we're short of time. I want to finish this. So let's say Okay, so let's say I had a two-dimensional data and I had only 2 points. Okay, so the capital D is defining the number of data points and small d is defining the dimension of the data, which is written as a subscript. The number of data points are written as the superscript. So we do x1, x2, this is the first point. It's two dimension, x11 minus y11 and multiplied with its vector, same vector, because it's the norm, right? How can the norm squared be written? A transpose A is norm of A square. So that is what we have written. Remember? In the Indian norm we wrote this. Here we are just doing the square of that. Everybody with me? Yes or no? Okay. So we write that, then we do it for the other point because it says it is sum of all the points. So we do x1, x2 for the second point and similarly that. Now when you have to find the minimum of this inside function, what do? Make the gradient equal to 0. Remember the first order necessary condition, gradient equal to 0 means give you the candidate for minimizer. If you go to the second order, the Hessian, then it will tell you whether it's positive definite, then it is a minimizer. Correct? The same story is repeating which we did in regression in SVM. So when you do gradient, I am writing gradient with respect to y because y is my unknown, y1, y2. That is the point which I am trying to find, which is square Euclidean distance away both from x1 and x2. And x1 and x2 have two dimension, x11 and x12. Yes or no? So now what I do, I expand this. Once I expand this, I get the squares. Now if I take the gradient of y1 would be minus, this will be minus 1 and 2 will come and will come out this term. Everybody see this? Take this with respect to y1, 0. This respect to y1, 2 minus x1 minus y1 is here. And then this 2 will come in front. Remember this 1 and 2 are not squares, they are the data points and the subscripts are the dimension of the data. Is that okay? These are squares. These are not squares because I'm putting, maybe I should have put circles here to differentiate that these are data points. Is that okay? So you get the first thing. You do with respect to y2. When you do gradient with respect to y1, you get this. When you do gradient with respect to y2, this will be 0. y2 would be again 2 minus x2, 1 minus y1, 1 will come. This will be nothing, again 2, x2 minus y2, minus 1 will come. Yes or no? Okay, so now if I have to write this in a vector form, this is the vector x1, this is the vector y, this is the vector x, this is 2 by the way, this is 2. I'm not able to edit it here, but this is 2. Is that okay? So this is y1, y2 becomes a vector y, x1, x2 becomes vector x2, y1, y2 becomes vector y. Correct? And there is a minus 2 plus 2, minus 2 plus 2 which is coming here. I've put this as a vector, this as a vector, this as a vector, this as a vector. Everybody with me? So if I have to expand this further, I'll write this x1 minus y, 2 in front, and x2 minus y. So which means that I could write it as summation of x minus y, where x is changing with x1 and x2 and x3 and x4. The data points are changing. Yes or no? Everybody with me? I have not written it down because I have thought this is written in the slide. I have already written it, so I'm not writing it. Everybody comfortable? Should we move? So what we did, we went from this step to this step, which I just showed you. Now I expand this step. Now if I expand this step, it is minus 2 summation x, and there is minus 2 summation over x of y. Now y is independent of the x, so you will just add the number of summations of y's will just bring the cardinality of d, the number of points we have. You can think of it something like this, that so what you're doing minus 2 x belonging to D, and then you're doing y here. Y is a vector, है ना? This is what you're doing. So what you could do is you will say minus 2y will come out, and this will be x belonging to D and summation of 1. So this is nothing but if they are 10 points, this will be equal to 10, because just adding those ones. Is that okay? So that is why we wrote this as absolute D. Now the gradient has to be made equal to 0. You make it equal to 0, take this to the other side and bring it down this guy. So you will get y is equal to 1 over D, x belonging to 2x. What is this? Just the mean, so this is equal to u mu. Everybody got it? That when you are finding an exemplar which is square Euclidean distance away from everybody, it is the mean of that value. That's the representation. That is what is written here. Comfortable? Comfortable? Okay. What did I miss here? Can somebody tell me? I didn't show one important step. Correct. Who answered? Are you answering? All of them. I can't give you all chocolates. So Hessian, we just applied the necessary condition. What is the sufficiency condition? Hessian should be positive definite. If gradient is 0, Hessian positive, then it is a strong local minimizer. Remember? So now what we'll do, we'll see what the Hessian is. So look at this guy. This is the gradient. Now to find the Hessian, what we'll do, we differentiate each of the terms with respect to y1 and y2 and put them in a row format. If you do this respect to y1, you'll get 2. If you do this respect to this whole thing with respect to y1, what will you get? Minus 2, minus 2, minus 2, minus 2, plus 2, 4. You do this with respect to y2, what you'll get? 0. You do this respect to y1, what you'll get? 0. You do this respect to y2, you would get 4. So what is the Hessian? Bolo bhaiya. Yes or no? This is positive definite, because both the leading principal minors are so hence it is positive definite. So this candidate which you got, it is a minimizer. It is not just a candidate for minimizer. Everybody with me? You lost? Okay? You stressed out? You can ask me. Any question? ये chocolate खत्म करो यार. Anup, question पूछो कोई? कोई question नहीं आ रहा? All right. So टाइम हो गया क्या? है 2-3 मिनट. So what did we prove? That arithmetic mean in the Euclidean space is the point that minimizes the sum of squared Euclidean distance to that data points. It is not just the squared Euclidean sum of the, it's not just the Euclidean distance, because Euclidean distance would then be with the square root. We are summing and squaring it, the whole thing. Correct? That is why it was written like this, the squared. The sum of squared Euclidean distance. Chale aage chale. The next part is more interesting. So now what we do is, we want to I don't know how much time. We'll stop here. This will not happen in a hurry. Tomorrow I'll tell you this. Whatever I'm telling you, there will be 4 questions with this tomorrow at the end. We'll finish this exemplar business. Basically, we are trying to find the candidate point. So we're talking about centroid. So where we are going is, you can see in this slide. What we'll do, we'll find the squared 2 norm centroid, which is the mean. Then we'll use a 2 norm without the square, which will be the geometric mean. Then we'll do 2 medioids. We'll do a 1 norm medioids, and so on and so forth. These are all representatives. They're real lives where centroids don't work, medioids works, where 2 norm don't work, 1 norm works. So this is where we're going. Once we have done it, we'll build a simple k nearest neighbor classifier. Once we have done that, we'll do more problems. And that is okay. Thank you.